Hi everyone and welcome. Today we'll see how to produce electronic circuits in Factorio. We'll see what type of buildings and what type of inserters that we use in order to produce that resource, how many of them we need in order to fill a single yellow belt which has throughput of 15 items per second, and we'll also see the different resources that are required in order to produce electronic circuits. We'll start with the number of assembly machines that we need in order to fill a single yellow belt. So a single yellow belt has a throughput of 15 items per second, and here we can see that an assembly machine of type 1 has a throughput of 1 electronic circuit per second. So how do we get to that number? Well, we get to that number by looking at the electronic circuit crafting time, which is half a second, and then we need to divide it by the crafting speed of the assembly machine, which is 0.5 as well. So it means that we can have one electronic circuit every second. It also means that we need 15 of those assembly machines in order to fill a single yellow belt, because 15 times 1 item per second gives us 15 items per second, which is the maximum capacity of a yellow belt. If we look at the required resources a little bit more in details, we can see that in order to craft an electric circuit, we will need 3 copper cable and 1 iron plate. So we will need to produce those resources as well. Given that it takes 1 second to craft an electronic circuit, it means that we will need those resources every second as well. So that means that we will need 1 iron plate per second per assembly machine and 3 copper cable per second per assembly machine as well. So that means that given we have 15 assembly machines, we will need 15 iron plates and we will need 45 copper cables. For the iron plates, given that we need 15 of them per second and a yellow belt can carry up to 15 items per second, it means that we need a single yellow belt in order to fulfill the consumptions. But for the copper wire, given we need 3 of them for a single electronic circuit, it means that we will need 45 per second, and given that we have only a capacity of 15 items per second for a yellow belt, we will need 3 of those yellow belts. That's what we've done here. We have 3 yellow belts that carry copper wire at their full capacity, and we have 2 yellow belts that carry iron plate. The reason why we have 2 yellow belts for the iron plates is because the yellow belts has only a capacity of 15 items per second, and the consumption of the assembly machines is 3 items per second for the copper wire. So that means that we can only fit 5 of those assembly machines per belt, and it forces us to create multiple lanes for those assembly machines, and therefore we need an extra iron plate belt. Now we're going to touch upon the inserters. The choice of the inserters depends on different factors, including how many items it can stack. Here we assume that a yellow inserter will stack only 1 item, and therefore it wouldn't be enough to fulfill the consumption rate of the assembly machine, which led to using fast inserters in order to insert the copper wire and the iron plate, and the use of long-handed inserters in order to move the electronic circuit that's been produced to a yellow belt. By having 5 assembly machines per line, it means that we have 3 lines, which is an odd number, and therefore it means that we have 2/3 of our productions on the right side of the yellow belt and 1/3 on the left side. That means that we will need to rebalance our belt, and this is why we used a rebalancer here. Now we're going to see how much power is required to run this setup. So we can see that in order to run an assembly machine, the maximum consumption is 77.5 kilowatt. So given that we have 15 of them, we need to multiply that number by 15, which gives us 1162.5 kilowatt. To that number, we also need to add the power consumption of the inserters. So we have 2 fast inserters that consume 59.3 kilowatt and 1 long-handed inserter that consumes 21.4 kilowatt. If we sum the consumption of those 3 inserters, we arrive to the number of 140 kilowatt that we then need to multiply by 15 because we have 15 of those assembly machines, and that gives us the number of 2100 kilowatt. If we sum up the power consumptions of the inserters and the assembly machines, we will arrive at the power consumption of 3262.5 kilo. The assembly machines don't only consume power, they also produce pollution, and in this case they produce 4 of pollution per minute, which means that for the 15 of them they produce 60 pollutions per minute. Now that we've seen how to produce 1 yellow belt of electronic circuits and that we know the resources required, we will look at how we can meet the copper wire's consumptions. Let's start with the production rate of one assembling machine. So here we can see that one assembling machine will produce 2 copper wire every second. We need 45 of those copper wire per second, which means that we need to divide this number by 2 because we can have 2 of them per second per assembling machine, which gives us the number of 22.5. So we can't have 22.5, so we need at least 23, and here for simplicity we put 24 of them. Here we can only have a maximum of 7 assembling machine per belt. We are not limited by the input here, but we are rather limited by the output, because given we produce 2 copper wires per second, we cannot have more than 7.5 assembling machines, because otherwise that would go over 15 items per second produced. So here, to keep it equal over all the different lanes, we put it to maximum 6, but it can go up to 7 per single yellow belt. Regarding the input, so the copper plates, we will need 1.5 belts. Here we have 4 belts because we have multiple lines, but in terms of quantity produced, we need 1.5 belts, and that's because here we have we need 22.5 assemblies, which consume 1 copper plate per second, which is 22.5 copper plates per second, and a yellow belt can only carry 15 items per second. So we would need half a yellow belt extra in order to fulfill that demand. So that's why we need 1.5 yellow belt of copper plate. Similarly to the electronic circuits, here we have fast inserters. That's assuming that it can only carry 1 item at a time, and in that case the speed of the yellow inserters wouldn't be enough to fulfill the demand. Here we have 4 output belts for the copper wire, but we only need 3 of them to produce the electronic wires. So what that means is that we need to rebalance them in order to merge those 4 belts into only 3 of them. In terms of power consumptions, these assembly machines consume each of them 77.5 kilowatt, and we have 23 of them. We have 24, but let's assume we have 23 of them. That means that we need to consume 1162.5 kilowatt to run all those machines. We also need to take into account the power consumptions of the inserters. So here we use fast inserters. It means that they consume 59.3 kilowatt, and we need 2 of them per assembling machine. So we need to multiply that number by 2 to have the power consumptions for 1 assembling machines, and then we need to multiply the number again by 23 to know the total power consumptions for all the inserters for the 23 assembling machines, and all of that gives us 2727 kilowatt. When we sum up the power consumption from the assembling machines and the power consumptions of the inserters, we arrive at the power consumptions of 4510 kilowatt. This pollution only produced by the assembling machines, and each assembling machine produces 4 pollutions per minute. So if we multiply that number by 23, that would mean that we would arrive at 92 pollutions per minute produced by those assembling machines. We've seen previously that we need 22.5 copper plates per second to produce enough copper wire. The production rate of a copper plate is 0.62, which means that we need 36 electric furnaces to meet that demand. It takes 24 electric furnaces to produce 15 items per second, and therefore to fill a full yellow belt, which means we cannot have more than that number on a single copper plate belt, or we would have idling furnaces. 2 yellow belts would suffice for the copper ore, but it would mean that our productions would be unbalanced. There would be more copper plates on one side than the other, and it would need to be rebalanced. So for simplicity, we kept the same number on each side. We have used normal inserters here instead of fast inserters because they are fast enough, even though as we can see they are configured to only carry 1 item at a time, but that is enough to meet the demand. Once the copper plates have been produced, they will be on 2 different yellow belts, and we need 4 of those yellow belts in order to produce the copper wire, so we will split them with 2 splitters. In terms of power consumptions, we can see that 1 electric furnace consumes 186 kilowatt maximum, and we have 36 of those electric furnaces, so we need to multiply that number by 36, which gives us 6696 kilowatt for the power consumptions of the electronic furnaces. We also need to take into consideration the power consumptions of the inserters. So here we have normal inserters which consume 15.1 kilowatt, but we need 2 of them per furnaces, and we have 36 of those furnaces, so we need to multiply 15.1 by 2 and then by 36, which gives us the number of 1087 kilowatt. For the pollutions, the electric furnaces produce 1 pollutions per minute, and we have 36 of them, so that would give us 36 pollutions created per minute. To produce copper plates, we need copper ore. The resource would normally be available on the map. To mine this resource, we need drills. In this case, we will use the electric mining drills. How much copper ore do we need to meet the demand? We know that 1.5 yellow belts of copper plates need to be produced, and it needs 1 copper ore to produce 1 copper plate. Therefore, we will need 1.5 yellow belts of copper ore as well. An electric mining drill produces 0.5 copper ore per second, which means we need 45 of them to meet the demand of 22.5 copper ore per second. Here, if we look at the electric mining drill, we can see that here is 0.7 per second, but this is because there's a productivity bonus of 40%. If you look at the base mining speed, it is 0.5 per second. That would require 1.5 yellow belts to carry 22.5 items per second, so we need at least 2 yellow belts. 1 yellow belt can carry the equivalent of the production of 30 electric mining drills. If more drills are placed on the same belt, some will idle and reduce the throughput. Most of the time, those resources will be transported by train, but depending on the configuration of the belt, they might need to be rebalanced. Electric mining drills don't need inserters. They directly feed the resource on the belt. This will reduce the power consumption. To calculate the power consumption, we only need to take the consumption of the electric mining drill, 90 kilowatt, and multiply by the amount we need, 45. It gives us a total power consumption of 4050 kilowatt. The electric mining drills produce a lot of pollution compared to the assembling machine. They produce 10 pollution. For 45 drills, that's 450 pollution per minute. We need 15 iron plates to produce 15 electronic circuits per second. The production rate of an iron plate is 0.625. It requires 24 electronic furnaces to meet this production. We cannot have more than that number on a single iron belt, or we would have idling furnaces. 1 yellow belt suffices for the iron ore to feed 24 furnaces. This is because their consumption rate for the iron ore is 0.625. If we divide the yellow belt speed, that is 15 items per second, by this consumption rate of 0.625, we get 24, which is the maximum number of furnaces that can be supported with a single yellow belt. We need 1 belt of iron ore to meet the electronic circuits demands. We also need 1 iron ore to produce 1 iron plate. Therefore, we need a single yellow belt of iron ore to meet that demand. Even if the quantity of iron plates produced can fit on a single yellow belt, we need 2 belts to satisfy the electronic circuits production design. To achieve that, we use 2 belts with a rebalancer because 2/3 of the production is required on the left-hand side and 1/3 is required on the right-hand side. The inserters will be the same as for the copper plate production, as the consumption rate is the same. Regarding the power consumption, the calculation of the power consumption will be similar to the one of the copper plates as well. We will take the power consumption of each furnace, 186 kilowatt, and multiply it by the number of furnaces, 24, which gives us the number of 4464 kilowatt. Then we will sum the power consumption for the inserters. The power consumption for one inserter is 15.1 kilowatt multiplied by 2 because we have 2 inserters per electric furnaces. And we have 24 furnaces, so we multiply it by 24 as well. It gives us a total power consumption for the inserters of 724.8 kilowatt. We then need to sum up those two numbers, 4464 kilowatt and 724.8 kilowatt, which gives us 5188.8 kilowatt, which is going to be the total power consumption. The electric furnaces produce pollution. They produce 1 pollution per minute, which adds up to a total of 24 per minute. To produce iron plates, we need iron ore. Just like the copper ore, the resource would normally be available on the map. We need 1 yellow belt of iron plate to be produced, and just like for the copper plates, it needs 1 iron ore to produce 1 iron plate. Therefore, we will need 1 yellow belt of iron ore as well. An electric mining drill produces 0.5 iron ore per second, which means we need 30 of them to meet the demand of 15 iron ore per second. That requires 1 yellow belt to carry this quantity. It can carry the equivalent of the production of 30 electric mining drills, which is exactly what we need. To calculate the power consumption, we take the consumption of the electric mining drill, 90 kilowatt and multiply by the amount we need, 30. It gives us a total power consumption of 2700 kilowatt. Electric mining drills produce 10 pollution per minute. For 30 of them, that means that we would have 300 pollution per minute. Now that we have seen what is required to produce one yellow belt of electronic circuits, let's take a closer look at how much power it requires and how much pollution it produces. The electronic circuits production requires 3262.5 kilowatt and they produce 60 pollution per minute. The copper wires production requires 4510.3 kilowatt and it produces 90 pollution per minute. The copper wires production requires 4510.3 kilowatt and it produces 90 pollution per minute. The copper plates production requires 7783.2 kilowatt and it produces 36 pollutions per minute. The copper ore production requires 4050 kilowatt and it produces 450 pollution per minute. The iron plates production requires 5188.8 kilowatt and produces 24 pollutions per minute. And finally, the iron ore production requires 2700 kilowatt and produces 300 pollution per minute. It gives us a total of 27,494.8 kilowatt for the power consumption, which is the equivalent of 459 solar panels, 31 steam engines or 5 steam turbines, and we have a total of 960 pollution per minute.